Oh shit, did I forget record? Oops, my bad. Okay. So this is the energy conservation for the electron. And this is basically what you have to learn for photoelectric effect. Well. Everything else can be used, it can be derived from this equation. So maybe one question that they can ask for SPhO is like plot a graph of Vs against F. Okay, wait, I haven't explained what Vs is. Okay, so Vs, right, is the stopping potential. So if you remember from your electrostatics, when you have a potential difference across these two plates, right? Then let's say this is the minus and this is the plus. When the electron goes towards the minus, the negative plate, the negatively charged plate, then it obviously slow down because it gets repelled by this, right? So what the stopping potential is basically defined as the minimum amount, like the potential at which there is no more current. So let's say I have some photoelectrons that are being emitted, right? They have some energy. Let's say they have Ke. So these electrons that have kinetic energy of like Ke, then they will they will be unable to reach this plate if this potential difference is of Vs. Okay, and Vs would be equals to like Vsq equals to Ke, which makes sense, I hope. If you guys like don't understand any part, you just like ask lah. Just unmute and ask. Okay. And Q is in this case the charge of the electron. So this is just again like another conservation of energy, I guess. So if your Ke is lower than this, then after that, obviously, then it won't have sufficient energy to reach this plate. So what happens is it will go here, then you just turn back and then go here, right? But then if the kinetic energy is larger than this potential difference times the charge, then it will just reach here. Then there'll be current. Yeah. If not, if it doesn't reach, then there'll be no current lah, because then the electrons cannot reach the other plate. Yeah. So this is what the stopping potential is defined by. Yeah. So then, okay, let's go back to this question. If they ask plot a graph of Vs against F, right? So we can link this here and then say that this is VSQ equals to HF minus, and then this is basically like a linear relationship lah. Vs against F. And this kind of makes sense, right? So essentially what is the case is that if I were to increase my frequency, that means the photon itself is just more energetic. Maybe I do like, I don't know, okay. It's more energetic, right? Then now the electron will fly off with a lot more energy. And so since it has a lot more energy, then you need a larger potential difference to stop the electron from reaching the other plate. Yeah. And okay, if you want to find the work function of the metal, which is again um defined as like basically the minimum amount of energy to leave the surface of the plate, you can find this would be the y intercept. Yeah. So if I were to draw the graph, right, it would probably like this. Yeah. So then if you extrapolate, this would be your I phi over q, 5 over q, yeah, 5 over q. And if you just times it by q, then you can get this lah. Okay. So this is like the photoelectric effect. Okay. Then this is another graph, which is like photoelectric current over actually I don't even know what this. Yeah, this is the potential. Okay, so maybe I can just like elaborate a bit on this because there was things someone asked about this before. So maybe I can start with this lah. So any potential that is more negative than the stopping potential means that the electrons won't be able to reach here. So then obviously the photoelectric current is basically like this current lah. And if, as I mentioned, if it's more than the stopping potential, more negative than the stopping potential, then there'll be no current. And if it's not as negative, then you can imagine that the electrons do reach the other plate and there'll be some current. Then if your potential is positive in this case, right? If it's positive, if it's at least sufficiently positive, right? Then all the electrons that emit from here will be instead attracted. So even if it's like, I don't know, like that, then you'll still get attracted and come here. So in this case, if it's positive, it will reach saturation current, which means that any electron that is emitted from the surface will end up in the other plate. So that will be like the max current lah. And the only way you can increase the saturation current is by intensity. Okay, I'll come back to this soon. So what I want to say is that this saturation current is independent of your frequency, because even if you increase your frequency will only, as I've mentioned before, frequency will only change this excess kinetic energy. The frequency does not change the saturation current. Okay. So I guess maybe I can talk about what intensity really means if you are looking at light as a photon. Okay, so intensity is defined as like power over area. Is it? I think so. Watts per meters. Yeah, okay. Yeah, power over area. So you can maybe split this up more lah. If you are looking at a flashlight, right? Hitting like a, actually, if you're looking at this is the surface of the metal with surface area A, then you got light that is hitting. Okay. So then you can think of power as the rate of energy that is being transferred to that. So dE dt over A. Okay. So then you can think of dE dt, right? Essentially, it's just the number of photons that hits this plate times the amount of energy that each photon carries, which is HF. I hope this makes sense because this is d dt, because this is like the total energy that hits the plate per unit time, which is equals to the number of particles times the energy that each particle carries. Okay. So that's why I mentioned before that if I were to increase the intensity of my flashlight, that means that I'm increasing the number of photons that's hitting my thing. And so, unlike frequency that does not affect the saturation current, if I were to increase my intensity, then you realize that the number of photons that is hitting my plate increases, and consequently, the number of electrons that is emitted also increases. And so, my saturation current will be higher if my intensity is higher. Okay, so I guess if you are looking at what to remember for photoelectric current is just this one main concept, that light the photon. And secondly, the difference between this diagram, this graph and this graph. So just don't get confused lah. One graph is more about frequency and how frequency affects the kinetic energy of the electron, whereas this one is more of saturation current, meaning like the max amount of current that you can get, which is dependent on intensity. Maybe I can just draw, this is I2 and this is I1. Okay. Okay, this is, I guess, the second concept that you can learn, which is matter waves. Basically like de Broglie's hypothesis lah, which is that this is true. Okay, so what this man said is that since light, which is originally thought of as a particle, sorry, a wave, which light was originally a wave, is now a particle. So what if all particles are also waves? That's a big brain now. Okay, so um, and this is the relationship that he derived. Okay, I don't know how much is derived, because this feels pretty like first principles. Okay, so all you have to remember is that for any particle with momentum p, you can have a wave that has wavelength of lambda as such. And this is like the proportionality constant h. Oh, by the way, I think my lambda is like reversed, which is something I can't like fix. So if you find it annoying, like too bad lah. Okay, so this is the second concept, which is de Broglie's wavelength. And I think previous lesson was relativity. I hope you learned that the momentum of light is equals to the energy divided by c. Then if you put this inside here, you actually get back E equals hf. So maybe you can think of this as like a more general form to this. Yeah. So the key thing to remember is if you have any, maybe even an electron, let's move away from electrons. If you have like, let's say football that's moving at some momentum, you can technically find what its wavelength, its imaginary wavelength. I shouldn't say imaginary because it does exist, but it's de Broglie's wavelength lah, which is this. And where this would be useful is um let's say we have electrons, right? It's true that when you shoot electrons to a double slit, you also get a diffraction pattern. So then in this case, you would need to convert your electrons into a matter wave, and then that's how you find your diffraction pattern. Yeah. So how you do that is you find the momentum of each electron. Then after that, you find its wavelength, and then after that, you use this wavelength for any calculations that you do with otherwise if it was a light, right? If it was a light, you would use like some wavelength, right? So now in this case, you use this wavelength. Yeah. So just substitute. So okay, so then this is I think it's pretty okay question. Does anyone need me to elaborate on this? Okay, I will take that as a no. Okay, so this is concept three, which is I think pretty standard lah. I think we have all learned this in chemistry, which is that if you have some atom and then you have a nucleus inside, then there's like electron shells. And so if you have an electron in like shell one, you can give it some energy and then it'll excite and then you'll go to shell two, excite, then go to shell three. Um, yeah. Okay. So essentially what you have to remember in this is basically spectrums lah. So I think we'll skip the hydrogen atom for now. We go to spectrums. So you can learn there's three types of spectrums. Firstly, we got the continuous spectrum, which is basically light directly shining. Then you get all these lights. Okay, so then next we have emission spectrum. Okay, so I'll elaborate on what emission spectrum is. Okay, so as I mentioned previously, we've got, let's say we've got the excited state atom. Okay, shouldn't be a problem. Okay, let's say this shell one, this is shell two. This is the nucleus, and this is the electron. If the electron de-excites, it will lose energy lah. I don't think I mentioned it before, but if you go further out, the energy level increases. Over here it's negative. Okay, actually I should elaborate on this. Okay, you can think of this as like a a, a well. Yeah, a well. Okay, so this is like at at the most outermost shell, you have basically zero energy. The more closer you go to the nucleus, which is positively charged, and your electron is negative, then the energy possessed by the electron, or I guess the electron and nucleus together, is gonna be some negative. And you can imagine like these are two like attractive of each other. And so if you want to pull this away from this closer shell to a further shell, then you need to put in energy. So you need to supply energy so that this electron can be pushed from this inner shell to an outer shell. I think that should be covered in chemistry. And likewise, if a electron is going to be removed, sorry, not removed, if an electron is going to move down the shell, if it's going to go from a shell 2 to shell 1, for instance, then energy will be released. And this energy is released as a photon. So if it moves down, then this energy, like let's say from here to here, comes down here, then you realize that energy is released because now it's more negative. So energy is released, and this energy release is basically a photon. Yep. And this photon would be equal to the difference between these two energy levels. Yeah. Um, I guess the important thing for this all this is basically like being careful and counting which to which it goes down to lah. Okay, and then as I mentioned before, the spectrums. Emission spectrum is basically when you have excited state atoms, then they de-excite, and then they emit this kind of photon. So then you'll be one like then your photons, right, are basically very specific. The energy that they possess is strictly only differences between two energy levels. So they cannot be the thing is that they cannot de-excite to a half a level. They have to go from here to here. Or when they excite, they cannot excite to a half a level or like, I don't know, come here. They must go from here all the way to here and all the way here. Yeah. So that's the thing with electron shells. Okay. Mm, I don't know if we should be learning Compton effect lah. I think that one is not necessary for SPhO. Okay. Maybe we can try this question. Question 2.2. Actually, wait. No, you shouldn't do 2.2 yet. Hold on a minute. Okay, wait. Maybe I should cover the hydrogen atom first. Yeah, give me a sec. Okay. So I just mentioned about excited atoms. Okay. So hydrogen atom. Okay. Basically, the thing that you have to remember is that this is the condition that has to be met. This is like the additional constraint that has to be met, which is that the angular momentum is quantized, and it is a whole number multiple of h bar. Maybe I can elaborate on this if I have time, but for now you can just take this as given. Angular momentum, which is mvr equals to nh bar. So this is condition one. Next, this is the Bohr atomic model, which is like a simplified model. And I have seen a SPhO question that asked me to derive from like basically first principles from this one and from this to obtain the energy levels of the basically get the exact numbers for these. So I think it's important that we know how to derive this. Okay. So condition one, as I mentioned, is basically angular momentum is quantized. Um, and then second thing that you have to know is you can think of this like a orbital mechanics kind of thing, lah. So this is your, I guess, a moon, and then this is your planet, your Earth. So the thing is, there will be a attractive force, and then this is in rotation. And so your for this to be in stable configuration, the centripetal force required should be equal to the Coulomb's force, lah. So this is the second condition that this is your Coulomb's force. Yeah, let's just say like Fe, your electric force, electrostatic force. And then this is your centripetal force that's required. And then this should be numerically equal so that this will stay in circular uniform circular motion. Okay, then this is all just like some algebra because you have essentially two unknowns, V and R, and then you have two equations because everything else is a constant. And so you can derive R in terms of essentially N, and then you can also derive E lah. I think you can just follow the steps. If you need any help, you can ask me also. Um, did anyone um face any problems with example 1.3? Okay, I guess that's a no. Okay, so I hope everyone is like comfortable with this solution and you should be able to derive this solution. I feel like this is something that they can test. You don't have to memorize this, of course. You can pretty easily get this result just from the fact that MVR equals to NH bar and the electric force equals to the centripetal force. It's just that now since we are talking about a nucleus with Z protons, so then your electric force will be different now. If you just change your electric force, you should be able to get this modified thing. And then if you sub all your Z equals to 1, then this is 1.6 times 10 to the power of 9, negative 19, mass of electron, all the constants. Then you'll get that this entire thing is equals to I think negative 13 point something over n squared electron volt, which is correct because we got this. Yeah. I sub in 1 because if it's a hydrogen atom. Yeah. Okay, so maybe you can try this example. It's essentially lithium 2 plus cation. Or what are the energy levels of the electron that what are the energy levels that it can possess? Mm, okay, should I give you time to do it now, or is that a waste of time? Okay, never mind. You just do this in your own free time, lah. I think we can just cover the other content first. Okay, so coming to the other spectra, I already talked about emission spectra, which is when you have an excited state atom, then it de-excites, and it releases the photons. Which makes sense. This is the emission spectra, this one. This is the emission spectra because we've got excited. This is the excited atoms. They de-excite, then they form these emission spectra. And each of these lines should correspond to one of these like lines, which is basically like each fall, because these are the emission ones. Then a bit more confusing is the absorption spectrum. So for absorption spectrum, you can think of it as like we have the detector, we have a flashlight, and then we have a gas. We have, I guess, hydrogen gas or some gas. In this case, if I were to remove this gas, then my thing would be essentially the continuous spectrum because there's nothing in the middle. I would just see this light, so I'll be seeing the continuous spectrum. But then now, since I have this gas, what happens is that the gas will absorb the light that specifically has this energy levels. So as I mentioned before, the electrons can only move up in discrete steps from that are such that the energy difference is equivalent to the difference in energy levels. So photons that have energy of this specifically this um value will be absorbed. And you may be asking, even if it absorbs, right? Like let's say I have some photon that corresponds to this energy level, even if it absorbs, so then this type of photon is completely gone, then won't it be re-emitted? And then it will come back, the same photon will come back, and then my eye will see it. Okay, but the problem is that all these ones, right, they will directly come from the source. But then when the gas absorbs this specific energy level, and then it will emit, which is correct. It does emit that same energy level again, but then it will emit in all directions. So what happens is that the intensity of this significantly decreases. So that's why when it's relative to the other ones, which is unphased, like if it's, let's say, if I were to choose this energy level photon, right? It'll just go in. Since it's not a exact difference of anything, maybe this, like the one I selected was like this energy level. Since um it's not exactly equals to any difference in energy level, so it won't get absorbed and it will just pass through, and then I can see it here. But then since this one corresponds to an exact energy difference, so it will get absorbed, it will get emitted in all directions, then the intensity will be less, and so you see it as a dark line. Yep. So absorption spectrums result in dark lines in a like a bright continuous spectrum, whereas emission spectrum is a dark background with just a few lines. Okay, this one is the X-ray spectrum. Okay, X-ray spectrum I think this one is a bit different. Okay, so this one I also have to remember because I haven't done this for a very long time. Okay, so X-ray spectrum, there's two different spectrums that are superimposed onto each other. We have okay, I don't have to pronounce this, Bremsstrahlung. We have this spectrum, which is the continuous one. Essentially, it's this part, yeah. And this exists because, actually, I don't even know the origins of it. I think it's like some, okay, basically, what is the case is that when the electrons decelerate, is it electrons or? Yeah, I think it's electrons. when the electrons decelerate, so when it's like, let's say it was at 100 meters per second, and then it decelerates and then becomes 10 meters per second. So when it decelerates, then this energy loss is basically given out as photons. And these photons exist in the X-ray spectrum. Their frequency is as such. So that's why they call it the thing, this braking radiation, because when the electrons decelerate, then they release this um, photons that have X-ray frequencies. So that's how the Bremsstrahlung radiation or Bremsstrahlung spectrum comes. Then the thing that we are more interested in is the the characteristic peaks. Okay, so let's draw back the atom. And okay, this one you shouldn't be confused because the mechanism for this is a bit different than the emission and absorption spectrum. So in this case, what happens is that when an electron flies about, it hits an inner electron, and this inner electron completely leaves the atom. So it does not go to another shell. This electron completely leaves the atom. It's just gone. So what happens is that when this electron is emitted out, now there's a empty shell, or I guess you can just say there's a spot lah. There's a spot there, and so a more electron in a higher energy level is able to move down. So I hope you can see the difference between this and an absorption and emission spectrum. Emission spectrum is the electron here moves up to a higher energy level. That's absorption, and then the emission one is a high energy level comes down. But in this case, it's because this electron just completely leaves the entire thing. Then after that, this electron moves down. Yeah. So this Ka corresponds to this electron moving down to here. Okay, so this is pretty annoying, but something you have to memorize lah. I don't know why they still, this is like some old convention that they had, which is that the first shell is K, then the second one is L, then it goes K, L, M, and OP. Yeah, and then alpha is when it moves down one shell, beta is when it's moved down two shell, I guess gamma is when it's moved down three shells. So that's the convention. So if they were to give that this is L alpha, L alpha means K L. That means that it's this one because it moves from it moves down one shell, meaning it's alpha, and then it goes to the L shell, so it's L alpha. So if I say L beta, that means it's beta. Then it would be from here all the way down to here. That would be L beta. So that's what you have to keep note of. Um, that's about it for X-ray. Yes, this one is if you don't understand yet, okay, I guess I can elaborate a bit on this also. So there is a minimum wavelength that the Bremsstrahlung radiation can have, which makes sense lah. So as I mentioned before, Bremsstrahlung radiation is just a braking radiation, which is like when the electron has some energy, is moving very fast, then it stops. So in this case, what is the maximum amount of energy that this radiation can have is when, let's say, all the electrons have some energy E. So all of these electrons, then one of these electrons in a singular radiation, in a singular step, it goes from all the way from E to zero. So it stops completely. It's like become in rest lah. So then the radiation has energy E. So meaning HF is equals to E. And if you realize this is the maximum lah, anything else is smaller than E. So let's say here, and then it comes to E over 2. This electron has E over 2. Then you realize that obviously this energy difference is only smaller than that. So the maximum energy difference is E, which is the initial energy. And so F is equals to C over lambda. So lambda equals to HC over E. Yep. So then you see that there is a minimum when this is as high as it can go, then this will be the smallest one. Yeah. So that's Heisenberg uncertainty is low-key kind of gay. Okay. But I think it's okay lah. So basically this is another concept that you have to memorize essentially, which is that the you cannot measure the speed of a particle, the momentum of a particle. You cannot measure the momentum of a particle and its position with absolute accuracy at the same time. So delta X and delta P over here are the uncertainties in the measurements. So if you have some uncertainty in X, and then after that, if you have uncertainty in X, you fix the minimum uncertainty you have in P. So let's say we realize that we have a delta X, right? Then delta P would be more than or equals to this, meaning it has to be more than this value. You cannot be less than this value. Yep. So I've given some like illustrations to give you some visual aid, but I don't know how much of this is like physically true. Yeah. So there's actually like quite interesting questions that they can ask with this. I haven't seen it in any SPhO paper yet, but can possibly ask. So if you do come across any interesting questions, do highlight it. I think that's about it for content-wise for quantum. So as you just saw, if you haven't like done this topic before, there's a few new concepts lah. Maybe concept one is that light is a photon, and then we did energy conservation to get this expression, and then we talked about the two different diagrams, right? One about the stopping potential and another one about the photoelectric current. Then the second concept was that we have the de Broglie's wavelength, which is that any particle can also be thought of as a wave. And this is the expression for that. So this is, maybe I can just highlight the things that you have to memorize, the formulas that you have to memorize. So this is formula 2 that you have to memorize. Technically, you can derive this from formula 2 itself. So maybe I'll write this as formula 1. This is the first formula you have to memorize. Then concept 3 was that we have electron shells, right? And then electron shells, as you go further away, the energy level of the electron shell will be larger. And don't get confused by the larger numeric value here because this is negative. So it is true that it's becoming more positive, meaning the energy level itself is larger. Yeah. So you do need to put in energy so that the electron moves up the electron shells. And when the electron shells goes down, then it releases energy. So that's concept 3 on electron shells. And also we learn about when the electrons do de-excite, then they release the photons. And likewise, when a photon hits the electron, then it can excite and then go up. And also to reiterate that the electron shells are quantized and the photons that get absorbed and also the photons that do get released, emitted, they have to follow this energy differences. They can't be in between. Okay. Then concept four is angular momentum conservation. So this is, I would say, the second formula that you have to memorize. Um, Angular momentum is conserved. Okay, so then this one you should. I don't think you should memorize. I mean, you shouldn't need to memorize this because this should be like second nature by now, hopefully. And maybe you can, if you haven't tried yet, try proving this result so that you can get familiar with this Bohr's atomic model. As I mentioned before, they have tested this before, so don't think that this will not be tested. Yeah. So they asked this question essentially like from step here all the way to here, they asked us to derive. So I think there's value in I mean not memorizing, but in doing this question once so that you know what to do. Then if you have done this, then just try this one also. Okay. Then I guess the last concept would be Heisenberg uncertainty. Yeah. Um, Honestly, I also don't like this Heisenberg uncertainty. I don't think they have tested it before, but I think it's good to know so that even if they do ask, then you can do. Okay. Then the spectrums is pretty much you just know lah. It's pretty much common sense, right? Because you can kind of just like you just thought experiment and then you can get all this stuff lah. So should be eight. Okay. It's 4:52 now. Maybe we can give like a 8-minute break before we start on nuclear. And I think nuclear is there's less content. It's pretty much one formula. Then you just have to use the formula in different ways. So that one should be hopefully shorter so that we have like some time. I'm expecting at least 30 minutes that we can do one or two questions. Yeah. Okay. We meet back at 5. And if you have any questions now, you can ask. So I can, yeah. way. I hope everyone's back. Okay. Nuclear. Okay. Before I start on nuclear, um, just thought of some things that maybe I wanna highlight with respect to Heisenberg uncertainty. Many cases, they won't tell you what exactly delta X is. Sometimes they do, sometimes they don't. In the cases they don't give you what delta X or delta P is, sometimes you have to assume. So there's one question that I have seen before. It's basically a single slit diffraction. Then they shoot particles, and then they ask you what is okay, maybe part one can be what is delta X. In this case, delta X is this slit width, right? They didn't explicitly say that delta X is the slit width, but you have to assume that delta X is slit width, right? Another question is if you have if it's a particle that is constrained in some okay, the specific example that I saw was electron being constrained inside the nucleus, which is absurd lah. But if the electron was constrained in the nucleus, then what? In this case, the nucleus, this is the delta X. Yeah. So this is basically some things that you have to kind of assume, and if only if you have done this kind of questions and you have been exposed to it, then you would realize lah. I mean, honestly, I wouldn't have thought that in a split this would be delta X lah. But then this is like things that you have to kind of assume and know. And also another thing is, um, for some reason, sometimes when you do find delta P, you might need to assume that this is your minimum momentum. So let's say we have a question with some delta X, particle emits out, then they say, okay, find the minimum momentum. And for some reason, minimum momentum is basically your delta P. I don't really know why, but this is like, I guess, exam tactics lah. Yeah, this is most of the case. This is true. But then of course you have to think about it like if there's some other way to get P min, then that'll be the better way. But if there's really no like that, okay. Okay, so this is I guess an add-on on Heisenberg uncertainty. Okay, we will go to nuclear. I think I kind of penned down everything that I thought of for this in words already lah. So I'll just supplement it. So essentially what you have to know is this singular formula. This is pretty much the core thing in nuclear for SPhO. And I'll skip the 1.32, 1.33. Okay, so let's say you already take this as a given lah, which kind of makes sense also. So it's just saying that your rate of decay, so you have some nuclei. This is nuclei, not atoms anymore. This is nuclei because it's nuclear physics, yeah. So if it's nuclei, the rate at which they decay or the population, the rate of change of population, my bad, the rate of change of population. So you have 500 of these nucleides, right? The rate at change of this population is going to be proportional to the population itself. So if I have 2 times the population, then my decay rate will be 2 times, right? If I have half the population, then my decay rate will be at half. Makes sense. And of course, since it's decay, meaning if I have 10 that decay, that means that 10 is lost from my population. So it's a negative sign. So the rate of change of my population with respect to time is proportional to the population itself. Okay. These two sections are basically one way to derive this, not really derive, but motivate the result out. I'll do that if I have time, but that one is mainly for your own reading. There's little actual practical value for your SPhO, I feel like. Half-life is basically defined as the time it takes for the population to be halved. So a simple practice, you can derive half-life in terms of your decay constant. This is your decay constant lambda. So I guess that's a practice that you can do. Before that, I hope everyone is able to solve this differential equation. I guess can do a simple practice right now. dn over lambda equals to, dn over n equals to lambda dt. Then if you were to integrate both sides, then you get ln n, your initial conditions, n naught, n, then this is 0 and t. You get n over n naught equals to t, and then n is equals to n naught e to the power minus lambda t. Okay, if anyone is unfamiliar with this, just call out, then I'll elaborate on this. Okay, so then if you want to do the half-life, you just say, okay, n is going to be half of n naught. Yep, this is the original. This will be the half of that. N naught e minus lambda t. And so then basically half ln equals to negative lambda t. And so your half-life is equals to ln 2 over lambda. Yep, so t equals to ln 2 over lambda. Okay. If they do give you information of the half-life, don't always try to find your lambda instantly, because sometimes half-life is just easier to work with. So I gave an example where half-life is very nice to work with. So I gave you an original population of 1,000. Then, over here is mean lifetime. Mean lifetime. Okay, maybe I will have to elaborate on what mean lifetime is. I think you would know what mean lifetime is if you followed the previous example. Okay, I'll go to that soon lah. I'll go to that later. I think this one is more important to SPhO, which is basically forming your ODEs. I think I can't remember the exact year, but there was an SPhO question which is I would say like a hard nuclear question, I guess, because nuclear questions don't really get that hard lah. So the question was basically that there's some nuclide population, but then there's multiple ways to generate the nuclides. Then there was also the nuclides decaying and all. So the thing that you have to remember is you'll just think of it as a discrete time step. So in this delta t time step, you just find all the different sources that produce the nuclide, and also all the different ways the nuclide can be removed. So this, of course, can be the nuclide itself decaying, in which case then it will be a minus lambda n factor. Maybe it is physically removed from the system at a constant rate of r naught. So maybe this is like 100 nuclides per second. Like some guy is inside and then he's removing the nuclides. Yeah, I don't know. This one is more simple. It can be some other thing, like some nuclide A decaying into nuclide B, in which case, if you are talking about nuclide B population, then we say that because of this guy's decay, because A is decaying, it becomes B. So then there's a generation of nuclide B. So then in this case, there can be some lambda n, in where this is lambda A and A, because this is the decay of the nuclide A. Then, of course, there can also be some source, right? Some source that is producing 100 nuclides per second. External sources, not some other thing decaying and then becoming this, but this is an external source. So you just have to consider all the changes. Then if you take t approaching 0, then you can find the derivative, right? So then that's how you form your ODE. Forming the ODE is the difficult part. And have you guys learned what integrating factor is? Anyone? Just saying if you know what integrating factor is. Maybe it's quite relevant. I can go through what it. Oh, you know. Is this something that you have gone through in previous physical, or is this like the first time you have heard this? Okay, somebody say something, bro.
I don't think it was in previous physical lessons.
Okay, maybe I can go through. Okay, integrating factor, specifically for the nuclear physics. I'll just, okay, so where you would use your integrating factor is, okay, let's say we have nuclide population A and nuclide population B. This is dn dt, it decays into B. Okay, so A decays into B, and then B decays into something else, doesn't matter. So if we do D, make it bigger, okay. D equals to, this one is pretty simple, because this one only decays. So there's no source, there's no other production, it just decays, pretty simple. This one, we already know we just derived it. So we know Na is equals to, let's say Na naught and E lambda T. Okay, maybe I should write lambda A T. Okay, so this is your Na. And now D and B dt is equals to the decay of itself, right? There's a decay term. But since every time A decays, it becomes B. So we have to write this, right? Not sure if you're familiar with the term activity, but so this would be termed activity of A, right? So the amount that is the rate of decay of A is equals to the generation of B, because each A decays into B. That should be common sense. So this is your ODE, right? Solving this ODE it looks okay. Maybe you can just do a separation of variables, but then if you realize this one is okay, but this NA itself is actually like this, right? And so this is a bit problematic, right? This is pretty problematic. And you can't do separation variables for this. It's not possible. And so this is where you would use you use integrating factor. And integrating factor is a bit like quite nice. So what you do is, firstly, you push all the NB and the NB dot in one side. And then there's the rest of the terms here. Okay, then what you do is you times both sides by e to the power of lambda b, and you would see why that is the case soon. So if you were to times e to the power of lambda b, okay, wait, I think I just wrote all the things here. Maybe you can just follow the steps. So we times e to the power of lambda 2t here, which is basically a b here. So we are doing 1 decays into 2 decays into something else. Okay. So in this case, we have, if we times all both sides by this would be true. And so then the special thing is you realize that this actually expands into this. So if you do like if you expand this out, you will get this. And that's why we times it by this specific thing. It's because when you do, if you differentiate this, you get back this. Yeah. So the whole point of the integrating factor is so that you can bunch these two terms into a nice thing like this. And so with this, then you integrate both sides. Maybe you can like in your own free time, you can try doing this integrating factor at least once. So essentially you just integrate both sides with respect to, it's a bit weird if you've never seen this before, but do get comfortable with this. Then the other side is basically just dt, which is okay. So the initial condition here, the reason why it's like this is because why it's 0 here is because we assumed n2, initial population of n2 is 0. So then it'll be basically 0 times e to the power of 0. So it's 0. And then over here, it's n2 times e to the power of lambda 2t. This side, pretty okay, normal. Then you expand this out. And that's how you get the expression for your n2. So in this case, the integrating factor is quite important. Yeah. Another way you can do this is by doing a non-homogeneous solution. So you can do the general solution. Then after that, you do a particular solution, and then you can get the same result also. So there's two ways to do that. If you don't really like integrating factor, you can stick to your homogeneous and particular solution technique. So that's the integrating factor, and that's about it for decay ODE lah. But I think for SPhO, most likely it will be something like separation of variables. So if you don't understand integrating factor, it should be fine. The more important thing is being able to form your differential equation in the first place. Yeah. So secular equilibrium is unlikely to be tested in SPhO lah, but I can still introduce. Basically, the thing is that let's say we have A goes to B goes to, okay, no, we'll do in numbers. We do in 1 goes to 2 goes to 3 and so on. In the case that your nuclide 1 decays very, very slowly. So this one decays so slow compared to all these, the other ones. So your parent nuclide is very slow in decay compared to your daughter nuclides. The daughter nuclides instantly decay. So they are much faster. In the time scale of your parent nuclides decay rate, your daughter nuclides are much faster. In that case, lambda 2, which is much greater than lambda 1, because I just mentioned that your daughter nucleus decay at a much faster rate. So lambda 2 is much greater than lambda 1. If you sub this in here, if you do approximations, right, you would arrive at this result. This one, I think you should. When I like derived this on my own, I think it was quite satisfying and gave me some like better intuition lah. So I think this is like a problem that you can try on your own to get why all, not just like the second nuclide, but also the third nuclide, fourth nuclide, fifth nuclide is also true for any nuclide. Yeah. So you can try this. And this is the result, which is that the activity of any daughter nuclide is equal to the activity of the parent. So if my parent has a activity of 50 decays per second, and this is when you're in like after a long period of time, then your daughters will also have 50 decays per second. Yeah. Okay, so this is, I would say, the next important part of nuclear physics, which is mass defects. And basically, energy release lah from formation of nucleus. Okay, so the concept here is that when you have 10 protons, actually, no, in this case, 2 protons and 2 neutrons that are infinitely far apart. So they are separated. They are nowhere near each other. And then if you were to measure the mass of this using a weighing balance, you would get this mass. But if I were to put all of this together and form a helium nucleus, then my mass is actually lower. So, and this is experimentally found that, what happens is that when you combine nucleons, which is basically either protons or neutrons, then their mass decreases. And I think if you did do relativistic dynamics, this is a result that you can kind of derive. So, and it's, I mean, a pretty famous equation lah. So I don't think you should need to memorize this. E equals mc squared. So this is basically an observation of E equals mc squared. Okay. So why is this an observation of E equals mc squared? We just realized that mass has decreased when nucleons are attracted to each other. So let's go to a different example, right? So, I mean, this is a very hypothetical case. So let's say we have Earth and Moon. Moon is very far away. And let's say if we move the Moon closer to Earth, then of course there's a decrease in the gravitational potential energy, which makes sense, right? Because the distance between the two bodies are lesser. So your potential energy has decreased. And this decrease in potential energy would be reflected as a decrease in mass. So essentially what this is saying is that if you basically mass is a measure of the amount of energy in a system. So in this case, since the energy of the system decreases, the mass of the system decreases. Likewise, in this case, when my nucleons were infinitely far apart, the energy of the system was larger. Whereas when I combined it into a helium nucleus, the energy of the system has decreased, and so the mass of the nucleus has decreased also. Yep. A common question would be, that doesn't make sense because protons are both positively charged, and so they will repel each other. So technically, I would need more energy. I will supply energy to the system so that I can even pack the protons together, and neutrons don't have a charge. So basically, I'm pushing two like charge together. So wouldn't that mean I give energy to the system? But that is true. But then the thing is, it's true that there is some repulsion between the protons, but then there is another force called the strong nuclear force, which only acts at a very short range. And this is attractive in the short range. So this is basically attractive in short range. So because of this force, there is a net energy release. Net energy release. There's a basically the system's energy has decreased. So you can still think of it as like the gravity case lah. So there will still be energy release because there is an attractive force when it's very short range. So all you have to remember is that the energy of the system has decreased, and so the mass decreases. This is something I learned in SO. Is completely not necessary for SPhO. Yeah, I, I I I put this here so that you can have an idea of what exactly is the difference in this mass, right? So following this, right? So the mass defect itself is basically the difference between the mass of the nucleons alone compared to the combined mass of the nucleons. So that's the mass defect. And you can find the binding energy. Binding energy is basically defined as the energy released when basically the energy released because of this reaction, when all the nucleons combine and then they form a nucleus, then they release that energy, and this energy is the binding energy. And basically binding energy is equals to mc square, where the m is the delta m here. Yep. This is again a bit more common sense lah. So this is the Z is the number of protons times the mass of each proton, number of neutrons times the mass of each neutron, and then you minus the mass defect, and then you'll get the mass of the nucleus. Okay, so yeah. Okay, so this is one way to find. It's not accurate 100%. It's a approximation, and you can basically approximate the binding energy of a nucleus. So this is, if you plot this, right? If you plot this, actually, if you plot this divided by A, which is the atomic mass, so it's EB over A, you'll get this, right? You'll get this graph where basically it's shows basically the binding energy per atom like the number of nucleons, right? And the peak of this, there's a stationary point here, is about, I don't know, 56 to 60, I guess. Yeah. And this is basically the most stable, which is where iron falls, iron and I think nickel also. So which is why iron is like considered most stable. Um, I leave it as a practice for you to convince yourself why this stationary point is considered the most stable. And stable meaning least energy in the system, the lowest energy configuration of the system. Yeah, you can think of that yourself. Q value is basically like basically if I have a reaction, right, a nuclear reaction, I have A plus B becomes C plus D. Then if I were to find the net change in mass of the entire system, so in this case, the net change of mass would be basically D plus C minus A minus B, right? And if I realize that this is negative, meaning the final mass is actually lower than the initial mass. That means mass has decreased, right? Mass has decreased. The mass of the system has decreased. Then energy is released, which makes sense because the mass of the system has decreased. That means the energy of the system has decreased. That means since energy is conserved and the energy of the system has decreased, that means energy has been released. Yeah. So yeah, if the mass of the system increases, Q value is negative. In this case, Q is the energy release lah. But let me think if that's correct. Mass of the system increases because more massive. Then your mass of the system increases. Yep, correct. If Q value is negative, that means energy is given to the system, which is why That means energy is absorbed, which is why the system has mass increased. Whereas if the mass of the system decreases, then your Q value would be positive, meaning energy is released. So Q is basically the energy release lah. And also do note that delta M here, which is delta capital M, is not the mass defect of a single nuclide, but the net change in the mass of the entire system. So there's multiple nuclides. Maybe there's even like a F here or something. And so it's the net change in the entire system's mass. Yeah. So don't get confused by delta M. Okay. Okay, finding Q itself is like pretty standard. There's nothing much they can do. But you must remember to use this Q. So this is where this is where the Q will be useful, which is if there's like some collisions. I think this is something that they can test because it's basically kinematics, right? It's basically collisions. Sorry, not kinematics, dynamics. Basically, it's collisions. But then now energy is not conserved. The energy of the system can actually be less, or the energy of the system can be more, and you also can calculate how exactly the energy changes. So, which is why I think it's pretty testable. This is something that they can test. So, you should know how to calculate Q and also use Q. Okay, I think this one you can read through yourself. Okay, so this is like basic collisions lah. I think you should have learned this in dynamics. Basically, what's this is that the sum of kinetic energy in the final is equals to the sum of kinetic energies plus Q, which is, as I've repeated, is basically the energy released, right? So if I have some positive Q, okay, technically I think this should be minus. Should this be minus? Because if Q is positive, that means energy is released from the system. Yeah, I think Q should be in this case, it should be minus Q. Wait. Q or collision control energy. Okay, it's fine. Just think of this as common sense lah. So if you have A and B, right, becomes C and D, and let's say the mass of the system has decreased. That means C and D is of lower mass. That means energy has released because there's the mass of the system has decreased. Meaning, like, you can just think of it as the mass that was once the some nuclear force potential energy is now converted into kinetic energy, right? So since the mass has decreased, then this Q goes into the kinetic energy. So I think this is correct. Yeah, this is correct. So if energy is released, then this energy is converted, is used as kinetic energy. So to reiterate, if your mass of the system has decreased, then this release in energy is used as the kinetic energy of the particles. Yeah. And likewise, if the mass has of the system increases, that means this is more massive, then the kinetic energy is converted into some potential energy, which is why it increases the mass of the system. Okay. So that's okay. Okay. This is like a relativistic form. This one is the classical form. I can elaborate if you guys are confused about that. This one is okay. I guess I can just briefly talk because you guys should have just learned about relativity last week. Okay, so I hope you guys are familiar with the Lorentz boost. I don't know if you guys learned about the momentum version, but this is also true. I heard that you guys were confused by the relativity lesson. Maybe this might also be confusing, but essentially, you can find your energy in another reference frame. using the Lorentz boost and also the momentum in a different frame. And sometimes you might need to use this if your particle is moving at a relativistic speed, and then you consider the momentums in its own rest frame, which might be necessary, for example, in this example. So maybe you can try this example. If you don't know how the example, how to solve the example, then you can just ping me. Okay, we have about the 23 minutes left. I want to go through this question and this question, 2.7. I think those are the interesting ones. This one is also interesting. Maybe if I have time, I'll do this one. Okay, so the rest also, I feel like you should try I mean, okay, I've only given like nuclear questions because I low-key was unable to find some quantum questions. If you guys have any quantum questions, just send in the chat also so you guys can like work together or something. Okay, so we can start with this problem 2.5. Oops. Should I just... Okay. Okay. So the question is that we have some radionuclide which decays at a rate of lambda A, and it also secretes from the body at a rate of lambda B. Okay. So the question is, what is the probability that it decays inside the body rather than it decays outside the body? Because if it once it secretes, then it leaves the body. Then if it decays, then it decays outside the body. So what is the probability that it decays inside the body? Okay. So maybe I can briefly talk about this also. The motivation behind the decay law, so that you can understand also. So the fundamental principle that you can actually use this to derive your decay law, right, is basically that the probability of decay is a constant. Okay, so this might be a bit confusing. It's like basically what I'm saying is that if I only have one nuclide, the probability that it decays from E and dt is a constant. So this is the basic principle, the most fundamental principle. Okay. So as I mentioned, probability of decay is dt with some proportionality constant. We call it alpha here, but later we will derive that alpha is equals to lambda. So yeah, so this is basically just lambda lah. Okay. So the probability of decay is this. Probability survival is obviously 1 minus this, which makes sense because if it doesn't decay, then it survives. So 1 minus this. Okay, then for it to survive from, let's say, 0 all the way to t, right? Let's imagine that the nuclide is rolling a dice at every dt. This is a dt, this is a dt, this is a dt, right? It's rolling a dice at every dt. Okay? And so for it to survive all the way until here, every time it rolls a dice, it has to reach this outcome. It has to reach 1 minus alpha dt, right? Which is why it's, if you want to survive from until t seconds or t minutes, then you have to survive each dt interval, right? And in this case, n is basically the number of intervals, right? So let's say you got this. So this is the number of intervals. And in this case, I'm referring to this as this. So this is t. Okay. So dt would be basically t divided by n. So the number of intervals t divided by the number of intervals. T divided by the number of intervals. So this is this, right? And then now we substitute dt with this. And nicely, this entire thing is actually the definition of the natural number. And you'll get this. Very nice. So now you've got e to the power of minus alpha t. Eerily similar, right? Okay, so we do a bit more probability. This one I think is not as relevant anymore. You can look through it because it requires like some year 6 probability things, like binomial distribution. But basically you can derive this. But the point I want to go through is basically this concept of a constant probability and the idea that the nuclide is rolling a dice at each interval, right? I think that's pretty good analogy. So over here, we can think of this, right? Okay, this given that the drug undergoes alpha decay, right? So this is a conditional probability. I don't know if you have learned this, but so basically the probability that it undergoes alpha decay, given that it does decay at the end, right, is basically the probability that it decays inside body over the probability it decays. Maybe this might be a bit confusing, but if you do like some like maybe examples in your own head, I guess maybe hopefully it works out. Okay, so this is like the first step that you want to start with. So the next step is you want to find the probability that it decays inside your body. So the probability that it decays inside your body is the probability that okay, the probability that let's break it down first. The probability that decays inside your body at time t. So decay inside body at time t. Okay, so for this at time t, for it to decay at specifically time t, there's a few things that must happen. Firstly, it must survive all the way until it must survive, as in like it didn't decay via alpha until time t. It must also not secrete out of the body until time t. And then subsequently, it must decay in the next dt. So that means that, as I mentioned before, the definition of decay within a dt time frame is lambda a dt. And also, technically, it should also not decay. Sorry, it should not secrete during this. So this is the thing. If I were to expand, right, you realize that the dt squared term would be, you can cancel that out because it's too small. And so this is what you get. Okay. So this is the probability that it decays at time t, right? Next, the thing is that you want to find what is the probability that decays at all in the body. So you want to find not just at time t, but any time from 0 all the way to infinity. So what you do that is, because probabilities, you can sum the probabilities up, right? So you basically just integrate all these individual probabilities at each t. You just sum all those probabilities up. And if you were to integrate it, you will get basically lambda a over lambda a plus lambda b. Okay. If you were to integrate it from 0 to infinity. Then next, we also want to talk about the probability that it decays at all, right? And this one is pretty simple because the probability that decays is at t, for instance, is equals to just lambda minus lambda at times lambda A dt. Because now we are not even considering whether it secretes or not. We don't even care about the body. We are just curious whether it decays at all. And similarly, if I were to think about it as probability of decay from t from 0 to infinity, this would be equals to 1, which makes sense because it would have to decay, right? If you have a nuclide that is radioactive and your time frame is 0 to infinity, it would have decayed somewhere between 0 to infinity. So then your probability is 1. So to answer the final question, it will just be lambda A over lambda A plus lambda B divided by 1, which is basically, yeah. So this is the final answer for that question. Which is kind of nice because it's like the fraction of the, it's like a weighted average, kind of thing. Okay, so this one is a bit more tedious. Given that we don't really have much time, maybe I can just give like the thought process. Okay, first part was, I think I changed the ordering of the thing. So now it's derive the expression for steady state peak first. Okay. So the steady state peak, let's say is this one, right? Okay, let's say this is NS. This is NS also, because this is steady state already. Okay. So steady state, and the scenario here is that we turn off the source, then we turn on the source. We turn off the source, turn on the source. Okay. Yeah. So this is where you have to think about your differential equations. In the case that we do have the source on, that means it is producing, then okay, let's solve that differential equation. So we have dn dt, right, equals to obviously it decays, and it's also producing at S naught. Okay. S naught being 100. Okay. So now what we do is that this one we don't really need integrating factor because this one we can just do it by separation. Goes to dt, and then we can get L naught, ln minus lambda S naught goes to t, and I mean this because S naught is a constant, so you can do this by separation of variables. You can do, this would be from, let's do n naught to n, right? Okay, and then this would be okay. Okay, then ln plus S naught equals to e to the power of minus lambda t. L. Okay, you can separate this out. And then we get S naught over lambda 1 minus. Okay, so this is the equation. So let's say we've got some n naught here. If we have n naught here, then it would slowly climb up and then become ns, right? Okay, pretty straightforward. Then if there's no source and it's just decay, then it's even more simple. It's just n equals to n naught e to the power of minus lambda t, which is we have derived before. And also you can also sub in S naught equals to 0, and you'll get the same thing, which is also quite nice. Okay, so this is when there is no production, and this is when there is production, right? And since it's steady state, right, and this is like a good technique for any like steady state kind of questions, is that when you start with the steady state, then you go through the process, you end at the steady state again. So you have NS, right? We NS, and then with the NS, it decays. So okay, we start with NS. So we say N naught equals to NS, right? So we sub this here. right? Okay, let's make this a bit more neater. So let's say this is NA, and then this is N naught. Okay. So N naught decays into Na, then Na do this combination of decay plus production and then goes to NS. Okay. So let's okay. Over here, we start with N naught, right? Becomes Na, and then over here Na does this combination of things and then comes here and then becomes NS. Okay. We can sub this over here. So we will get NS is equals to N naught e to the power of minus 2 lambda t plus S naught over lambda 1 minus e lambda t. Okay, and because we said that it's steady state, so N naught is also equals to NS. So then we can sub here NS. And then if we do rearranging, we can get NS equals to NS equals to S naught over lambda 1 minus e minus lambda t 1 over yes. I hope that is correct. Okay. So that is that. So that's part one. Part two is that you prove that your initial condition does not affect the final NS. There is actually a few ways to do it. Okay, one way that I did was, and I mean, I'm not going to do the full solution, but just give you the thought process is that let's say I start with some N naught that is lower than NA. So we start with N naught that is this amount, right? And it's less than NA. Then we go through one loop. So we go through the loop of go up, then go down, right? And if we do this loop, we realize that N naught goes closer to this NA value. So we start here, and let's say the NA value is here, right? This is N naught, this is NA. Your ending value is going to be here, right? So it's going closer to NA. And then if I were to repeat this again, then you go closer, again closer. So if I keep repeating this, then it will keep going closer. And that will show that if you are below, if your initial population was below NA, it will approach NA. And similarly, if your initial population was above NA, then it will also decrease and then go to NA with continuous periods like this. So that's one way to prove it. I think there's probably other ways to do it also. I think the very interesting one is the alternative technique to solve part one. This one, I came across this question in INSO, and I didn't know how to do the alternative solution. Then my mentor taught me this, which is low-key very interesting. So basically, right, the idea is that, okay, let's say this is your steady state, right? Okay, we just ignore everything else. This is your steady state. This is the steady state population. Your steady state population at this point, okay, is a bit hard to articulate, but I'll try my best. Okay, so this steady state population is actually the sum of the generation of nuclides, the past generation of nuclides, right? So if by the time you reach steady state, right, your initial L naught would have already decayed to zero. Like none of your initial condition, none of your initial particles exist anymore. They all have died. So N or NS is strictly just the sum of the production of the particles from S naught, because we have a source, right? So NS is basically the sum of the particles that have been produced by the source. But the thing is, let's say we are looking at start from this. So this is how much that has been produced. This particles, let's say this is let's say there's 100 particles that's been produced. Okay. Let's just say 100 particles has been produced. Okay. And then we start from here and then we reach here. So this is the difference between this point and this point, and realize that from here to here, there's been 20 seconds, and in this 20 seconds, this 100 nucleides has decayed into 60, let's say. Similarly, we have also another 100 nucleides that's been produced by this. But then now, since they have survived 40 seconds before they are being accounted in this NS population here, right? So since they have been 40 seconds, they are older, they have decayed more. So maybe this one is I don't know, 48. I don't know. Okay. And likewise, this is also 100 that has been created, but then they have been alive for longer, they have decayed more, and so they'll be lower, 42. Okay, I have no clue if this is numerically correct. Okay, so the idea is that each time nucleides are being generated by the source, we can just take those nucleides and then put them in a separate bucket. So this one, okay, we put it here. This one, we put it in another bucket. This one, we put in another bucket. Okay, so we put them in a separate bucket. They decay on their own because decay is independent of anything else. They decay on their own, right? Separately, and then after that, we sum those up. Okay, so if I were to write this in math, essentially what this is okay, and we are ignoring this step. Okay, we are ignoring this one first. We will come back to this one. So anything beyond this, right? We want to sum all the contributions from each bucket. So so let's say this is a X, right? The how much is being produced from each interval by the source is, let's say, is X. Okay, X is being produced by the source, and then they are decayed for this duration, right? They decay for this duration, and okay, so let's say this is 1, this is 2, this is 3. The first one decays for this duration. The second one decays for 2 times of this duration. So you can just put all of that as n. So n equals to 1, and you can then put this. So the thing is, for steady state to be true, we must consider infinitely old things that have been generated and decayed and so on. So this would be summing to infinity. So basically we are summing each contribution, each past contribution that itself has decayed, and then we are taking all of those contributions and summing them up and then forming our NS. X in this case is basically just this. This is how much is being generated by each interval. So we can sub this in here later, right? Okay, wait. Yeah. So if you haven't noticed yet, this is basically a geometric series. You can evaluate the geometric series. Uh, um, then, as I mentioned, we ignore this one, right? We can now add this back, which is basically just x, just an x, right? Because this x hasn't decayed yet, so it's just a singular x. So we can just add that back. And so if you were to evaluate this, right? Let's just say x and then times or this would be okay. Technically, I mean, you guys have done geometric series lah, so you should know what I'm doing. Okay, this would be the geometric series. And yeah, if you were to evaluate this, you would get 1 over 1 minus 10 times x. And if you were to check, this is basically this. Yeah, so this is the alternative solution. Yeah, cool. Okay, so this I would say is like probably the hardest nuclear ODE type of question that you can come across lah. So you should be fine. You can try this question when you are free. If you have any trouble, you can ask me. Try this question also, so you can get familiarity with the concept of electron shells and energy differences. Yeah, and that's about it. As I've mentioned, it's really the content. You need to understand the concept, uh, have a firm understanding, so that even if they throw questions at you, you are able to um at least get some meta marks lah. Yeah, so I hope it's been helpful. I feel like maybe I could have given a bit more questions. If I do find a bit more questions, then I'll just upload in the chat also. Yeah. So I think I can pause the recording now. If you have any questions, then you just ask lah. I'll just answer any questions now. If you guys if you want to leave, then you can leave now. Right? Okay. Thank you.